Good morning to this director seminars. Today's seminar will be presented by Dr. John Plain from University of Leeds. He will talk about the cosmic dust in planetary atmosphere, and he will be introduced by our scientific director of Severo Ochoa and our vice director in science, Isabel.
Good morning, everybody. Thank you for coming. It's a pleasure for me to introduce you Professor John Plain. John Plain is Professor of Atmospheric Chemistry in the School of Chemistry of the University of Leeds, where he also is the Director of Research and Innovation and leader of the group of Atmospheric and Planetary Chemistry. I've got a whole page list of things that I'm not going to read. I'm just to be concentrated on the most outstanding among the outstanding lines of his CV. He graduated in chemistry in Jesus College in the University of Cambridge and took his PhD in physical chemistry with David Hussein, working on gas phase reaction kinetics and spectroscopy of atoms and molecules that are especially relevant in atmospheric, interstellar and combustion chemistry. John's research interests span a wide variety of topics, including different aspects of atmospheric chemistry of planets and moons, astrochemistry, and cosmic dust. His research on chemistry of the Earth's atmosphere extends from the marine boundary layer to the mesosphere, and encompasses the three branches of atmospheric chemistry, from laboratory studies and theory to atmospheric measurements and modeling. And a full list of models, models that have very important implications for comparing with the observations. He is recognized as one of the world-leading experts on the aeronomy of meteors and metals in the atmospheres of the Earth, of Venus and Mars. And his group also performs experimental and theoretical research on low-temperature chemistry that is relevant in molecular clouds in interstellar medium and in cold atmospheres such as Titans. In addition, John has carried out extensive field work at the Earth's surface. John has obtained over 25 major grants from British, European and American funding agencies. For instance, he got an ERC Advanced Grant for the project CODITA, Cosmic Dust in the Terrestrial Atmosphere, between 2012 and 2017. He has authored more than 340 papers. He gave the Royal Society of Chemistry Tilden Lectureship in 2006, and he has been awarded with the European Geoscience Union Award Wilhelm Berkels Medal in 2017 for his fundamental contributions to the study of metal layers in the upper atmosphere and the chemistry of biogenic halogen compounds in the marine boundary layer. So, you see. In today's seminar, John will describe the results of a large study designed to determine the input rate of cosmic dust to the terrestrial atmosphere, using a self-consistent treatment of cosmic dust from the outer solar system to the Earth's surface, and the extension of this work to Mars and Venus. So I'm sure we all enjoy John's seminar. Thank you, John.
Great. Well, it's a pleasure to be here. Thank you for the invitation to give a talk today. And I'm aware that this institute covers a huge range of activities and interests, so I'm going to try and keep this at a fairly general level, see how we get on. And this project that was just referred to really tried to answer a very simple question. How much cosmic dust comes into our atmosphere? And if we know how much it is, does it matter? So that's a very simple question. And when we started the project, the range of estimates, as you can see, was somewhere between 3 tons and 300 tons per day. And so that was clearly something that needed to be studied, and that was the point of the ERC project. here is a list of my collaborators currently at Leeds. This guy, you know, was a major part of the ERC project and is now an international collaborator along with Francisco from here. And then various groups. I'll be showing data from this group who work with the MAVEN satellite around Mars, and various other characters down here that you will know some of their names. Just to begin at the beginning, and I don't probably need to spend much time on this, ALMA made the first observations of a new protoplanetary disk around a young sun over here. And of course, these dark rings here are where the new planets have formed, and they've removed or mopped up the dust, which is what you can see here in this luminous ring. And in our solar system, we're obviously right here in the inner solar system. Between Mars and Jupiter is the asteroid belt, and then outside of the orbit of Neptune is the Kuiper belt, which is another major source of dust. And even further out is the Oort cloud, which now is a much more isentropic distribution, so it's no longer in the invariant plane of the solar system, are these other cometary objects which, again, enter our solar system every so often and are another source of dust. There are three different types of dust source that I'll be talking about. Jupiter family comets. So these are comets that have been captured. They originally started out beyond in the Kuiper belt, but they've been captured by Jupiter's gravity and now are making very short period orbits within the orbit of Jupiter here, so every 2 or 3 years. And this one, Comet Encke, is a major source of dust within the solar system, within our atmosphere. Then there is the asteroid belt, as I showed you, and some of these asteroids have orbits which take them well into the inner solar system here and are another source of dust. And finally, Halley-type comets, which have much longer orbits. So Halley itself has an orbit of 76 years, and these are mainly Kuiper belt objects from outside of Neptune. A comet, as you know, is not a nice white object. They're actually dark, very dark colored. Here is 67P, and there's a model of it with one of the co-discoverers, Churyumov. And you can see this really looks like coal. It has an albedo of around 3%. So it's absolutely full of dust. And when these objects move into the inner solar system, like this one, Comet Hartley, the vapor, various compounds like water and CO and CO2 sublimate, and these jets here are basically driving the dust embedded in the ice into the interplanetary medium, where they form a source of dust. And you might say, how much dust is there? Well, one interesting measure is between the Earth and the Sun. If you basically took all the dust and compressed it into an object, it would be around the size of the Moon. So there is dust around. And it's very easy to work out where in a planet meteoric ablation occurs. So this is where a particle entering the atmosphere will warm up sufficiently to melt and evaporate. And it's where the pressure is around 1 microbar, because the incoming particle will have hit enough air molecules to undergo frictional heating. And in our atmosphere, it's around 95 kilometers, which is in the boundary between the mesosphere and the thermosphere. This is the temperature profile of the Earth's atmosphere. It's lower on Mars, higher on Venus, and very high in Titan, because Titan is only a moon, so it has a very large scale height. And for a dust particle coming into Titan's atmosphere, it's almost like landing in a feather pillow, very soft, and very little ablation occurs in Titan as a result. So let's look at these estimates of the amount of material coming into the Earth's atmosphere. And this is a plot of the amount of sodium being injected from meteors, different ways of estimating it in tons per day. And we start off with the global model. So this is produced from NCAR's model Wacom that some people here work with. And in order to model the sodium layer that envelops the Earth around 90 kilometers, you need to put in a certain amount of injection, and it's a rather modest amount, as you can see here. And at the other end, there's an actual measurement of the flux, and I'll show you how that's done in a moment, which is about 10 times larger. Then there's an astronomical model, which is based on looking at the zodiacal cloud to work out how much dust is in the vicinity of the Earth at 1 AU, and there's also radar observations here. So that's not a very satisfactory picture. It's much worse for iron. So these are the tons per day of iron coming into the atmosphere, starting off with the global model, and then we have these other three ways of estimating it here, and then the amount of cosmic iron that is deposited in ice cores, which you see is 50 times bigger than this. So clearly there are big problems interpreting at least several of these ways of estimating this amount of input. And this big project basically was trying to look all the way from IDPs in the solar system, how they ablate in the atmosphere, give rise to metal ions in the thermosphere, neutral metal atoms in the Earth's mesosphere, meteoric smoke, I'll explain what that is in a moment, and then the chemistry of nucleating ice clouds, removing acids and so on, freezing polar stratospheric clouds leading to ozone depletion, and finally deposition at the surface. And what we wanted was one self-consistent model from the top, so an astronomical dust model all the way through an ablation model, a meteoric input function injecting into a whole atmosphere climate model, Wacom, from 140 kilometers all the way to the surface. So that was the strategy. And in order to test that self-consistent model, we needed observations of various kinds, which are listed here. So of the zodiacal cloud, meteor radars, metal lidars, rockets, looking at particles, satellites, various sorts of measurements, aircraft, and accumulation in ice cores at the bottom. And in Leeds, what we did was to use laboratory studies to inform various parts of this model. So how do dust particles actually ablate? How easily do different metals within a dust particle evaporate? Metal chemistry, looking at the kinetics of the reactions that control the metal layers in the mesosphere. We did a little bit of this, though not so much in the lab. And then we looked at how to freeze polar stratospheric clouds using what's known as meteoric smoke, or fragments of meteorites. And we came up with 6 ways to constrain this input rate, get the answer. Okay, how much comes into the atmosphere? One is to look at the zodiacal cloud. Another is to make radar or LiDAR observations of shooting stars, essentially, but these would be subvisible, so not the ones you can actually see using radar or LiDAR. You can do global modeling, as I just explained, using a model like Wacom of these layers of metals in the upper atmosphere. You can make vertical flux measurements, so actually look at the rate at which sodium and iron atoms are falling down through the mesosphere. And you can then go to ice cores and look for cosmic spherules. I'll explain what they are in a moment. And you can also look at deposition of meteoric smoke. Almost all of these involve things that happen in the atmosphere. The only one that is extraterrestrial is looking at the zodiacal cloud itself. So in order to look at understand any of these, you need to have a good understanding of how ablation occurs. And it's these two here, 4 and 5, that we ended up using in this project to get the answer. So here's a nice picture of the zodiacal cloud, and if you do a cut through it here and you measure the intensity of the zodiacal light, it's that black line over there. That's 0 degrees latitude in the ecliptic. And these lines here show the 3 sources I described: Jupiter family comets, asteroids, and Halley-type comets. And they all predict rather different distribution compared to that. The one that is obviously closest are Jupiter family comets. Asteroids come from too near the Earth, so they're much more concentrated in the plane of the ecliptic. And Halley-type comets come from too far away, so they are also they are much broader compared to the plane of the ecliptic. Now, how does a meteor actually ablate? Well, as it starts to enter the atmosphere, air molecules will just hit the surface. It's traveling at hyperthermal speeds. That means somewhere between 11 and 70 kilometers a second, and they will just knock off atoms and molecules. That's called sputtering. But the particle will heat up, and once it melts at around this temperature, sodium and potassium ablate, because they are quite volatile metals. Then if it makes it to around 2000 Kelvin, these three main constituents of cosmic dust ablate, iron, magnesium, and silicon. And if it then heats a bit more, the very refractory elements, calcium and aluminium, ablate. So that's the sort of basic picture. And in order to test that, we built a machine at Leeds, and this was led by Juan Carlos, where we could place on a filament here some fragments of meteorites, flash heat them to 2700 Kelvin, observe that using a very fast response pyrometer. So they're flash heated over just a few seconds, simulating atmospheric entry. And then we had two lasers here which could look at two metals, so sodium and iron, or sodium and nickel, for example, simultaneously at high speed, make a measurement 200 times a second. That just gives you an idea of the action. So there's the pyrometer and the lasers that are crossed through here, and so the filament is in the middle there. And if I just try to show this movie, if it will show, what you'll see here, yes, is there's the filament, and these little white balls are actually molten meteoritic fragments, which are maybe 30 or 40 microns in size. Just see if that will play again. Yeah, so you can see the filament's heating up, which is why you can see it. And by a lucky chance, the little balls run down the filament. They don't jump off it through a process we then discovered is known as electromigration. And here are some results. I'm going to focus here on nickel because I want to show you in a minute there's been a very interesting problem with nickel in the atmosphere. So what we have here are these red lines show the actual temperature of the particle, simulating entry at 14 or 17 or 20 kilometers a second and three different sizes of particles. So if you have a little particle and it enters close to what it would have if it was in an orbit following the Earth and just drawn in by gravity, then you see nothing happens at all. These orange and brown lines show sodium and nickel. No ablation here. If you now start to go faster, so the temperature profile you see is now getting up above 1700 at the peak here. You ablate sodium, but almost no nickel. And then you go faster, now you get nickel as well as the sodium. And if you go to bigger particles, they will flash heat to much higher temperatures. So this is getting up to 2400 now, because they have a lot of momentum to be stopped by the atmosphere, and you see plenty of ablation of both of these metals. The broken lines on here, orange broken, and the brown lines are a meteoric ablation model. It's called CABMOD that we've developed in Leeds. And this does reasonable predictions, not always so good, because there, for example, is the measurement and there is the model. But it turns out that if you actually look at a meteorite, and this is the Allende meteorite here, so here is an electron micrograph, and these show different elements. As you would expect, iron and silicon appear everywhere because a meteorite is basically an iron magnesium silicate. But if you look at, for example, nickel and sulfur, you can see there are a relatively small number of grains, and they are actually composed of iron, nickel, and sulfide. So the ablation modeling becomes a bit more complicated. You have to have two different types of grains in your meteorite. One is the main constituent, and then the other are these small profiles. So I've mentioned looking at meteorite or meteors entering the atmosphere by radar, and one way to do that is using this radar here, which is in Puerto Rico. This is the Arecibo Observatory, which, according to people who make measurements here, like Diego Hanches, is the best way to see meteors, particularly small meteors. There's one problem trying to understand meteor radar observations, and that's just shown in this figure here. This shows the probability here, so this is going from a small number up to 1, of a metal atom colliding with an air molecule and ionizing as a function of velocity. So as you would expect, sodium is up here somewhere, and something like atomic oxygen, which is much harder to ionize than sodium, you have to go to very high speeds to get a probability of greater, say, than 0.1. But the main problem is most of the dust is in this sort of velocity range here, and when the atoms evaporate, of course, you have a very steep slope here in log space, so any small error here leads to very big incorrect estimates of whether a particle is actually detected. So we decided early on that radars, although commonly used around the world, are not the way to measure the total amount of dust. So I've mentioned these metal layers that occur at high in the mesosphere, up here around 90 kilometers, and they're things like sodium, iron, potassium, calcium. These can all be measured from the ground by laser radar. And why are they there? Well, around this part of the atmosphere, above 90 kilometers, the atmosphere is chemically reducing for the first time. We live down here, obviously, in an oxidizing atmosphere, but when you get above 85 kilometers, you have a lot of H and O atoms, and these are chemically reducing. So below this, where you don't have a lot of these metals become oxidized to make oxides, carbonates, whatever. And when you get into the thermosphere or the ionosphere, there are lots of ions that charge transfer with the metal. So you have metal ions, metal atoms, and then compounds. And these compounds polymerize together to make meteoric smoke particles, or MSPs. These are nanometer-sized particles, which are mainly going to be metal oxides, iron oxides, hydroxides, and so on Earth, on Mars, probably carbonates. And these diagrams here show everything we currently know about the chemistry of sodium and of iron in this part of the atmosphere. And these diagrams are not made up. They're based on laboratory measurements in our group and by others, measuring individual rate coefficients for example, sodium reacting with ozone and NaO back with O. And you can see that you can, using water and carbon dioxide, you can make sodium bicarbonate, which you put into a cake to make it rise. On iron, the main constituent is this hydroxide over here. But eventually, some of these compounds form things like hematite, goethite, pyroxene, and these are the constituents of meteoric smoke particles. We can take that chemistry, put it into Wacom, and model the occurrence of, for example, the iron layer. So this is measurements at Wuhan in China showing month of the year and altitude. Here is this iron layer. You see minimum in summer. And it agrees very well, or the model is agreeing pretty well with here, so long as we turn down the amount of iron being injected. And this is the sodium layer at mid-latitudes in the US. So we can model these things well. The trouble is how much is actually being injected. Now, if these atoms are being injected by meteoric ablation, they must be coming down through this part of the atmosphere, because otherwise they would just go on accumulating forever. And you can use a LiDAR to measure the vertical fall rate and their concentration. And if you average that, they don't always fall, they're going up and down, but on average they're coming down, you can determine a vertical flux. And here's what it looks like. So the flux is negative because it's downwards, and here is sodium and iron, and you can see the flux maximizes here where you still have lots of atoms, and then it disappears because they're being oxidized. And you can use these measurements to come up with amounts of sodium in tons per day and iron being injected. And you can use Wacom to answer the question, at this altitude where you make the measurement, is all the sodium in the atomic form? Because that then gives you a flux of total sodium, and indeed it is. These are all the other compounds that are in the model, but you can see at this altitude it's all sodium. So that gives you a good estimate. Now the other thing you can do is measure cosmic spherules at the ground. This is the South Pole base, and underneath this base there is, so here is the base, and underneath it is a huge water tank which goes down over 100 meters, and this is where water has been melted for the base. These are cosmic spherules. These are cosmic dust particles that enter, melt, but don't completely evaporate. So they re-solidify to make little glass beads, which are very easy to detect. So what you do is basically take a vacuum cleaner, hoover up all of this stuff at the bottom here, and you can identify these cosmic spherules and count the amount coming in. And extrapolating globally, it's around 4 tons per day. So we have 3 fluxes now, sodium and iron at the top, and spherules making it all the way down through the atmosphere. We have an astronomical model called ZODI, which gives us the mass distribution, velocity distribution, and as you would expect, the asteroid, so this is the mass flux and velocity here. For asteroids which are coming from nearby, just beyond Mars, the velocities are low. They're a bit higher for the Jupiter family comets in black, and much, much faster for Halley-type comets from further afield, outside of the Kuiper belt. Anyway, you can take that information and just solve 3 simultaneous equations. The flux of iron is equal to the flux from Jupiter family comets, asteroids, or long period Halley-type comets. With 3 coefficients, you have the flux of iron and the flux of spherules. Solve the equation, and that gives you these 3 coefficients here, which is the relative amounts of each of these sources. In fact, it's the absolute amount, because you have absolute fluxes of 3 things. And we won't go through all of this in detail. This is the answer to the big problem. 28 tons per day, plus or minus about 14, is the total amount of cosmic dust coming into the atmosphere. So these are the 3 sources and their contributions of various things here. About 70% of that is coming from Jupiter family comets, and it's been lost on the bottom here. About 30% of that is ablating to generate these metallic vapors, which then make meteoric smoke particles. And you can basically look at the injections of all these different metals from the 3 different sources weighted by these coefficients, and this is the total over here. And I just wanted to pick out on here iron, which is the red line, and of course that's the main constituent here, along with silicon that's being injected. And this blue line here with the dots is nickel, which is obviously a lot less than the red line. Why am I interested in nickel? Well, because a few years ago, a group in Alaska made the first measurement of the nickel layer. Here it is in black, and this is the iron layer that they measured. So these are both, as you see, in the upper mesosphere. And there's something very, very surprising about this, which is how much nickel there is relative to iron. Essentially the same amount. And if you know anything about cosmic material, nickel is a much smaller component than iron. And that's as a result of nuclear fusion in a star. And so we then began a new project to try to understand what on earth was going on. Well, the first thing to do was get another LiDAR group to make measurements, and so this is what you get with a LiDAR. You're basically measuring photons that are scattered back to a telescope at the ground. This is a log scale here of your photon counts, and you see it falls exponentially with height. If we just look at this, which is the solid line here, which is corrected for the background, it falls exponentially and would carry on doing that, but if you tune it to a nickel transition, you suddenly get a fluorescence here. Clearly there's a layer over there, and here are a bunch of measurements that were made. This is operating in the near ultraviolet, a very hard frequency to work with because it's strongly absorbed in the stratosphere and by aerosol. So very hard measurements to do. 2 Chinese groups have been trying to make this measurements, and pollution in most parts of China is so bad they can't do it. So here are our measurements, and you might say, oh, you've got the same as the Alaska measurements, but notice that the difference in scales here. Here is the nickel concentration, there is the iron. It's 38 times more abundant, which is a much more sensible number. So the whole premise for our project has turned out to be a wrong measurement. Not the first time that's happened in science, of course. And you can also take rocket measurements. This is an analysis, in fact, Juan Carlos did. And these are measurements of ions. So you probably can't see that, Fe plus and nickel plus. There is the Fe plus layer, here's the nickel layer, and the ratio is very similar to what we predict from ablation, our ablation model based on the lab experiments I showed you, or just the cosmic ratio. So nickel is not really a big surprise or a problem after all. Knowing the amount of cosmic dust, you can now think about what it's doing in the atmosphere. One thing it does is creates layers of metal ions called sporadic E layers. These affect radio communications. This is up in the above 100 kilometers mainly. Very good tracer of dynamics and chemistry in the MLT, which is our main interest. Ice cloud nucleation in the mesosphere, I'll talk a little about. I don't have time to talk about that. Juan Carlos did a very nice study of sulfur chemistry. I will talk today about, that was published a few years ago in JGR. I will talk about PSC formation and freezing. And the injection of cosmic ion, it turns out, is very important in regions of the ocean which are ion deficient, like the Southern Ocean. And if people are interested, I can say more about that later. Noctilucent clouds. These are water ice clouds. Not reported before about 1885, and they seem to be almost certainly a good, an unambiguous indicator of changing climate in the upper atmosphere. What seems to have triggered them was this volcanic eruption. This is Mount Krakatoa, which completely blew up. This is the before and after illustrations, and this threw a lot of water vapor and dust well into the stratosphere, and that triggered the appearance of these clouds abruptly here. They then decayed a bit and then have been growing brighter, spreading to lower latitudes and so on in the last part of the last century and into this. So this is the volcano here, and then this seems to be the manifestation of climate change. NASA launched the AIM satellite to take pictures of them. This is a picture over the northern hemisphere. You can see Greenland and Iceland. So here are these clouds which occur mainly at high latitudes in the summertime. So this is the 1st of August last year. And it turns out that, well, the reason we think that they occurred is the very large increase in methane with the Industrial Revolution, which started here. And basically, once methane reached above a tipping point up here somewhere, the amount of water being generated, this is the overall reaction, it happens by radical chemistry, but the amount of water being produced in the middle atmosphere was such that these ice clouds became visible. But also, the upper atmosphere has cooled by about 10 Kelvin in the last 20 years because greenhouse gases act as refrigerants at low pressures, unlike down here in this part of the atmosphere. So the two things have combined to make these clouds much brighter. And it was shown very recently by Thomas Leisner's group in Karlsruhe that meteoric smoke particles, these little nanometer-sized silicate particles, are ideal nuclei for forming these ice clouds. Further down in the atmosphere, you can actually measure their extinction. So this is using the SOFI spectrometer on this AIM satellite I showed you a minute ago. And they can make measurements of extinction in solar occultation at 3 wavelengths, from the UV to the IR here. Obviously, the extinction is much larger in the UV, as you'd expect from small particles. And you can use that data to basically take pairs of extinction. So you can look at that over that, or that over that, or that over that, and show that this material, this meteoric smoke, which you see at very, very small extinctions, it's a wonderful measurement that's made, must contain iron. So it's something here, but you can see all of these possible candidates here all contain iron, because that gives the particle color, the brownish color of iron. Yeah, we can move on, I think, from that. Let's come down further in the atmosphere now to the stratosphere, and these are what are known as nacreous or polar stratospheric clouds. These occur during the winter in the polar regions. Chlorine is processed on them, and then in the following spring, ozone is depleted. So we have a lot of interest in how these clouds freeze and grow and create a surface on which this heterogeneous chemistry can occur. So, smoke is coming down, as I showed you, and we can measure it in the lower mesosphere using the AIM satellite. This is, what you're going to see here is a high-speed film. And this is a unique camera at the moment system, which can track this with very good resolution. So it's going to move up this way. The things moving that way are stars. And you'll notice that this is, let's see if it will work. There it goes. What I'd like you to notice here is that this is not, a little blob that's just evaporating. It's clearly fragmenting. This is still bigger than most of the dust that's coming into the atmosphere. Just play it again. So this is probably a few millimeters in size, whereas the particles I've been talking about are microns, tens of microns in size. But nevertheless, it's quite likely that some of this cosmic dust contains water or organics. So the little grains in the cosmic dust is probably glued together by organics. But these seem to fail. So the organics burn up or something happens to them. You can run the movie back and see at what point does this thing start to fragment. It's around 900 Kelvin. And if you take an organic, they're like tar, that you use for the road, they tend to break up around that temperature. And so this may be what's happening here. The grains are stuck together by tar. I mean, this is one of the big astrophysical problems, actually, is how do you get dust in a solar nebula to stick together and make planetesimals? And as you, I'm sure, know, one of the theories is that it's organics that coat the grains and then they can stick. And that may be what's happening here. So these are going to be bigger fragments, probably a micron or two. They don't spend a long time like nanometer-sized particles, which can take years to come down. These come straight down because they're relatively heavy at these very low pressures. So here you can imagine we have a cloud here of water nitric acid droplets over the pole in wintertime. And we have two sources of nuclei. One is the smoke. So this is where ablation occurs, the gas phase species polymerize into these little nanometer particles, and they come down the vortex in the wintertime in the polar region. Or you can have a cosmic dust particle which basically explodes because the organics glue fails, and these organics come raining down here, but by the time they get down to 25 kilometers, the pressure is enough to stop their fall rate, and they can spend a reasonable amount of time, by which I mean days to a few weeks, down here around 20 kilometers. And there's been a long-standing problem. How do you freeze a nitric acid water solution and make an ice particle? If you just make a concentrated nitric acid solution, put it in the freezer, it will not freeze. And it's quite clear from observation that these clouds freeze around 5 to 10 degrees higher in temperature. So we, in the lab, do an experiment where we have a bunch of droplets here, and these contain either a surrogate of smoke, which is fumed silica, as shown here, or fragments of meteorites. This is one example here, the NWA meteorite. 40% nitric acid, which is what you have in the stratosphere, polar stratosphere in winter. You start off here, drop the temperature, and you can see in the movie here, or the still from the movie, that some of these have frozen. Sorry, they're these ones here, the white ones. And you can just make a plot. What fraction of your droplets freeze as you lower the temperature of this stage? Obviously, you start off, none have frozen, and then if we just follow this line up here, eventually all have frozen. That's pure nitric acid, which is well below the temperature at which these clouds appear. And you can see by putting in different things here, so these are analogues of various kinds and bits of meteorites. Some of them really trigger freezing up here around where this is observed to occur in the Earth's atmosphere. So it does seem that these meteoritic fragments are a key to making polar stratospheric clouds and causing ozone depletion, which is a nice impact. Let's now think about other planets, and again we have worked on Venus. We've shown that in the lower atmosphere of Venus, where it's very hot, meteoric smoke is an excellent catalyst for oxidizing CO and removing molecular oxygen. And this is an interesting aside. The postdoc who was working on this said, well, you know, the lower atmosphere of Venus, where the temperature goes up to 700 Kelvin, is a bit like an automobile exhaust. Maybe this cosmic dust we're making in the lab could be an automobile catalyst. And so what he, now it's not too difficult to oxidize CO in a catalyst. Of course, the holy grail is to remove nitrogen oxides, which is all the fuss at the moment about, you know, scandals with Volkswagen and clean and air quality. And we've actually found that this special cosmic dust actually catalyzes NOx removal at room temperature, which is a big advance, because it's when engines are cold or people are stuck in traffic and their engines are not producing a hot exhaust that you get a lot of pollution. So that might be an interesting spin-off. But let's move on from Venus. Titan, I'll just mention, again, you can get really interesting chemistry there. Much lower temperatures, of course, on Titan. And what we found was that acetylene, C2H2, sticks on the dust and actually converts into benzene. So if you take C2H2, multiply by 3, you get C6H6. Very simple chemistry, and that goes on in the lower atmosphere of Titan. But let's focus on Mars. And we've been doing a lot of work with this satellite, as does Francisco here. And we became involved because in 2014, a comet called Siding Spring, which is an Oort cloud comet, so it's just come into the solar system once, it will not return. At one point we thought it would hit Mars, but it actually passed about 130 kilometers from the planet. You can see from this picture here, there's the invariant plane of the solar system. It's clearly an Oort cloud comet with a trajectory like that. And on board this spacecraft is an instrument called the IUVS, which is this imaging ultraviolet spectrograph, and it was basically able to measure the magnesium ions that are produced up here when Mars went through the fresh dust trail of this comet siding spring. So here's a spectrum in the ultraviolet. This is near ultraviolet here. Intensity. Here are various bands that you see in Mars' atmosphere, the Cameron bands of CO2 and so on. And after the comet arrived, it looked completely different. So if I just alternate these back, you can see something has obviously appeared here, a major spike, which is magnesium ions, magnesium here, and it's not so obvious here, but there is Fe and Fe plus as well. Now we can take this CABMOD model that I referred to earlier. We know exactly what the impact velocity is of the cometary dust. It's only one velocity, and we can model where in Mars's atmosphere these three metals would be injected from this siding spring dust, and we'll just focus on those two there. And this is a 1D model, the broken line compared with observations in the solid line, and we do a pretty good job for MG+. Everything is kind of tuned up to that. It's only a 1D model that we run in Leeds at the moment. And magnesium, not so bad. Iron, things are not looking quite so good, bearing in mind this is a log scale here, so some interesting problems with iron in Mars's atmosphere. And this is the model prediction. This is hours after the dust trail from the comet was injected, showing initially you get a very, very strong layer down here, and it very quickly is transported upwards by turbulent diffusion and so on, and then molecular diffusion. Mg you only have down here because there's chemistry that prevents Mg up there. It's ionized very quickly, and similarly for these two. And these are vertical profiles now of the Mg plus concentration. So there is the measurement and there is the model, and it starts off fine. That's only 4.5 hours after deposition. 9 hours, not so bad. We're sort of capturing the way you get this rapid transport over tens of kilometers through the atmosphere. But as you can see, when you go a little bit longer in time here, things are not very good at all. And the interesting question is, is this really where a 1D model fails? 1D is fine for a short time, but you really need a global transport model to solve that. But you can still, from the amount of magnesium ions form, you could think, what would a Martian on the surface have seen when the planet hit this dust trail? And actually, it would be very like a great Leonid storm that occurred in 1833 over the US. And this is a wood carving of what was seen. And as there would have been something like up to 120 visible shooting stars a second. I mean, it would have been a most fantastic light display. But no Martians that we know of on the surface. And it was too dusty for the rovers to take pictures, so that's a pity. Anyway, what about just the normal background dust that's coming into Mars's atmosphere? We can use our terrestrial model of what's being injected here, following this ERC CODITA project, to now work out how much is going into Mars's atmosphere. These are measurements of the background layer of Mg+, and this is the only metallic species that's been observed so far on Mars outside of the very special event of siding spring. I should say it's the first time a metal layer has been seen on any other planet, apart from exoplanets where sodium always shows up. That's the one thing you always see in these hot Jupiters and so on. I had published a model 5 or 6 years earlier, and we were able to fit that by scaling things a little bit. But we predicted a very large layer of magnesium atoms in Mars's atmosphere, and the detection limit of this IUVS instrument on MAVEN is here. Now, this unfortunately is a log scale, so you can see my prediction was terrible for the magnesium layer, and it's always fun to be shown to be wrong because you learn something, right? And you can actually, if you look at the spectrum here, so this is where you take an actual spectrum of Mars, the black line, and you fit all these known bands, the Cameron bands and CO2 and so on, and you take them away, you generate a bump here, which is at 280 nanometers, that's magnesium ions, but here I had predicted there would be a big bump due to magnesium, and as you see, there's nothing, sadly. And so the question is, where is all of this magnesium going? Well, start off, you need to know where is the material being injected. So this is now injection of these three elements for background dust coming into Mars. And it's not coming in at very high speed because Mars is a small planet, so the gravitational focusing is less. And so here are iron and magnesium, which we're going to focus on. So you were injecting magnesium directly where the magnesium ion layer is observed, but there's no observable magnesium. And so I had to scratch my head for a bit to come up with some explanation. So this is magnesium chemistry on Mars as we understand it. Ablation here should give rise to three things. First of all, magnesium itself, ions just through collisions with the CO2, and of course it could make MgO directly because hyperthermal magnesium atoms can hit a CO2 and just pull off an O to give MgO. And so we reckon that most of the incoming ablation is making either that or that and not too much of this. Because the problem is, in order to get rid of magnesium, you've only got two options. One is reaction with ozone, but there's not a lot of ozone in Mars's atmosphere, or charge transfer up here. And that we can compute and know reasonably well, but it's not all that fast. So using that chemistry, we are able to model this layer here. So these are, the symbols here are two different orbits of measurements of the Mg plus layer. Here's Mg, which is now at this altitude below the observable detection limit on Mars. Rovers have, from the ground, photographed these high-lying clouds, and these are very like noctilucent clouds on Earth. And they are between about 70 and 100 kilometers, and one interesting problem is, how on Earth can you condense CO2 onto something when the temperature is rarely cold enough to do it? You have to go to extremely low temperatures, below around 80 Kelvin, to condense CO2, even though obviously it's the main constituent of the atmosphere. So we looked at what might be going on here. This is what happens to magnesium in Mars's atmosphere. It forms something called magnesium carbonate, very, very polar compound onto which you can stick CO2 and water. If you are familiar with these units here, the dipole moment of these carbonates, sodium and iron, as well as magnesium, over 9 dBi. And you can take magnesium carbonate, it looks like a kite. You can add 3 CO2 molecules, so that's obviously easy in Mars' atmosphere. Delta G here is the Gibbs energy, quite negative, so you can do that, and then just switch with 3 waters, so knock those on, put on water, add 3 more waters, and you form a very stable cluster here of a magnesium carbonate with 6 waters. Now this is so stable that even at relatively high temperatures above 150 Kelvin, this will exist, and it polymerizes together. Clearly, for those of you who know, these are electronic structure calculations. These haven't been seen in the laboratory, but you know, These are relatively straightforward to do. There's no funny spin effects or anything here. So these Gibbs energies are pretty well known, and these should just go on making what we call dirty ice clusters. And we believe that these are the way in which you form these high CO2 ice clouds. And so the next strategy is to try to model that. Now, the ions on Mars can also be measured by something called the neutral gas ion mass spectrometer, or NGIMS, as it's known over here. And this shows the vertical profiles on 4 different deep dip campaigns. What I mean by deep dip, this satellite is in a very elliptical orbit. So if Mars is here, the satellite is going like this. Very, very elliptical orbit, and it can be arranged that when it is at periaps, it actually dives right down into the atmosphere, as you can see, nearly to 120 kilometers. And of course, if you only do this a few times, you conserve fuel and you don't end up burning up in the atmosphere. So what you see here is the background atmosphere in purple and 2 ions. And there are 2 very, very unexpected things to see here. First of all, you'll see that the ions have a very similar scale height to the neutral atmosphere. This goes against what we understand about ions in planetary ionospheres, because an ion is paired up with an electron. An electron has an infinite scale height, because it has such a low, effectively infinite, because it has such a small mass, and that has the effect of pulling the ions up, so their scale height should be twice that of the background atmosphere. On Mars, they're exactly the same. The second big puzzle, you have 2 ions here. This is mass 24, that is mass 56, so more than a factor of 2 different, and they're identical up here, whereas the lighter ion doesn't have so much gravitational attraction, so you should see a separation by mass, and it looks exactly the same. So Mars, full of surprises. Now, the last thing I want to show you is work we've done here with Francisco, and this is using the LMD general circulation model. So this is at the moment preliminary, but what we've done is to take this, and this is the only global model of Mars that I'm aware of that has ion and neutral chemistry in it. We've put in 22 magnesium neutral and ion molecule reactions, which I had validated in that 1D model I showed you a minute ago. And so the first thing I was very interested to see is observations show that magnesium ions peak, take my word for it, I'll show you another period of the year in a moment, but they peak around 8 a.m. If you don't believe me, here's another measurement in summer. You can see they peak at 8 a.m. And this is really weird, that a photochemically produced species, you'd imagine, photoionization, it should peak in the middle of the day over here, but it peaks at 8 a.m. How on earth could that be going on? Well, when we ran this in the LMD said straight away, yes, that is exactly what should happen. Here is this Mg plus layer, around 90 kilometers, peaking early in the morning. And what is the reason for that? Well, this little movie here shows the LMD results. Now, the top here is O2+. That is the dominant molecular ion in Mars's atmosphere. But because it's a molecular ion, it's short-lived, because electrons love to jump on it. Dissociative recombination destroys it. So this very definitely is photochemically driven. And this is just following the sun across the planet. This is degrees of longitude here. This is equatorial, that's height. Okay, so that's exactly what you expect to see. Here is Mg+. You can see it's doing nothing like that. It's basically showing 3 different patches here, essentially, which are not really migrating with the sun. And these non-migrating tides on Mars are caused by the very high volcanoes, which create very strong tidal effects and other things. And basically, that's why you get a completely different diurnal behavior. And the reason that this happens like that is because Mg plus is very long-lived. It's an atomic ion. So that was a very nice surprise to find. And if we compare with the Earth, this is measurements on Earth, latitude against month of the year, magnesium ions. You can see at low latitudes, not much seasonal variation. You get big summertime peaks. At high latitudes, we've got lots of sunlight because it's long days. So that is exactly what you would sort of expect. Now let's look at Mars, completely different. First of all, most of the ions are here at high latitudes. So this is because of very strong poleward transport. But also, seasonally, there's a very big difference between northern hemisphere spring over here and southern hemisphere summer over there, where there's a deep, deep minimum. And this seems to be, in the model anyway, is driven by strong vertical winds. This is the time when Mars is close to the Sun. It has a very eccentric orbit. It generates a lot of dust because there's a lot of turbulence and strong winds in the lower atmosphere. And this is pushing the magnesium ions up and results in this minimum. This we still have, as I say here in red, to be confirmed by observation, which may, of course, show this is completely wrong, but we will see. So let me conclude. We found the terrestrial dust input. Our current estimate's now around 28 tons per day, 70% of which is from these Jupiter family comets and 30% of it ablates. I'll just pick out a few of these other things. One thing we found, we believe, and we have to show this, is wind-driven vertical transport accounts for why the actual measured vertical transport of these metal atoms by the LiDAR, remember I showed you the metals falling down, is much higher than in a model like Wacom. It's because Wacom does not resolve small subscale waves, and these create a lot of downward transport that needs to be captured in the future. I've shown you MSPs, probably nucleic noctilucent clouds, and in particular freeze polar stratospheric clouds. This is something that we are still working on, is the deposition of cosmic ion and just how important that is as a climate feedback. And the last thing here, as I said, is Mars has made a very interesting contrast to the Earth, full of surprises which I wouldn't have predicted. Smallish planet, you know, obliquities rather like the Earth's, etc. So that's very nice, and maybe in a year or two, Francisco and I will have solved these problems at the bottom. Thanks very much.
Thank you very much for this very interesting talk. A lot of information to process. I like it. Questions?
Very nice talk, John. Just coming to the last slide or the last comment you made regarding small-scale driven vertical transport, gravity wave-driven vertical transport. So you mentioned that the metal layers can provide a constraint on the vertical transport, and Wacom, for example, it does not resolve these gravity waves, but it does parameterize them. So would you say that the parameterization in Wacom of the gravity wave driven meridional circulation is not good enough to
parameterize is the breaking of those waves and contribution to turbulence. I'm referring here to unbroken waves, still dissipating but not yet broken, and that can create an additional transport term which can be as significant as KZZ. So the way we are hoping to do this is Wacom, there's now developed what's called a regionally refined thing. So for example, over part of the US, you could take the resolution down to 12 kilometers by 12 kilometers. I mean, you cannot run that globally with chemistry, but you could for a region. And we hope to be able to show when we do that that if you can resolve waves down to 12 kilometers, this greatly enhances the vertical transport. And then, of course, it's not just metals, but things you're interested in, like NOx from the thermosphere, will also be transported down much more quickly. And atomic oxygen, and for understanding the air glow and all of that. So it is very important, I think, to resolve this question one way or the other, and the metals are an indicator that something is seriously wrong. Yeah.
Other questions?
Hi, well, really, thank you for this really nice talk. You've touched so many points and really illuminating many of open problems. I am fascinated by some of them, but I don't know so much. But looking a little bit to these puzzles that you mentioned in the Martian atmosphere, in particular, that surprising scale height of the ions. No? I just was wondering if some caution is needed there, no? Because if I'm not wrong, these deep campaigns come from, they are performed using very oblique entry trajectories. So maybe some caution is needed, when you build these scale heights. You might be going through really different latitude, longitude, and maybe not a real 1D action. No? I mean,
that's a perfectly valid comment. What is interesting is when I didn't show them here, but more recently they've done some over the southern hemisphere where there is remnant magnetism. And there you actually do see big layers, rather like sporadic E layers on Earth, where you can get magnetic fields concentrating things into layers. And again, it's quite difficult interpreting them for this very reason, that of course you're not really looking at a vertical profile. But all of the ones they've done so far seem to show this same effect of the neutral and the ions having the same scale height. And of course the two metals are measured simultaneously, so the fact that they seem to vary in the same way, I think that is a real effect, and this is something we're going to test in the LMD. Again, it may be due to turbulence extending a lot higher up than people have thought. There's this idea that you have a turbo pause, and above that you see some gravitational separation. This is the classical picture from the Earth's atmosphere, but it doesn't seem to work with Mars. So this is an ongoing problem to solve. Yeah.
Okay, well, it's a really very nice talk where you cover really many aspects, so that's really very interesting. I have a couple of comments. The first one is about the first question about the total dust input. I have a question about the temporal variation. If I have any annual variation or not? Is it just totally constant all over the time, or there is some period where we have a larger or the other are smaller?
The equator, it's fairly constant, but at high latitudes it maximizes in the autumn. So if the sun is over here and the Earth's coming around here, so it would be autumn in the northern hemisphere, you can see the northern hemisphere is ramming into the dust. So you get more in the autumn, and then when you come around this side, so it's now southern hemisphere autumn that maximizes. And then there are also variations with meteor showers, but from everything we've been able to tell, they don't make a big, so you have this constant amount, then you have a shower every so often, but it doesn't really make much of an impact. Partly because the material spends a week or two at least in the MLT, and so adding a bit for a day or two with a shower doesn't make a lot of difference.
Yeah. Essentially the driver because there was some kind of variability with the annual cycle.
They don't seem to make too much effect.
about sodium layer now, because there are people really looking at the exoplanet, and they had to remove the telluric contribution of that. So my question is, how variable is it? Is it dominated, in the source? We know that there is the variability because of the meteorology of the upper atmosphere, the gravitic waves, and so on. But there is the variability along the time of the sodium input is really large or not?
A lot of wave-driven, the gravity waves throw it around, so you get quite high-speed variability, easily within a factor of 2 over a few days.
But it's mainly due to the variability of the atmospheric itself, the dynamics, but not because of the flux.
Obviously you might have a helpful Doppler shift if you were looking at another planet, but otherwise, if you're outside the atmosphere, it's safe. And all of these exoplanets have sodium, because it's in a nice part of the spectrum, there's nothing else there. And if they're hot, of course, you have plenty of sodium just from the surface.
This question about the last point you made it there, whether if I would like to take a message home now, the difference between Earth and Mars, the main reason of that could be, what is the main reason? Is the composition of Mars? Is the temperature? Is the density? Or?
Well, it's definitely the CO2 atmosphere interferes with the chemistry of the metals, I think, because they form carbonates and so on. And CO2 is a much better ligand. But also, obviously, the thermosphere of Mars is rather cold, because CO2 is a good radiator. So, those are the big differences.
Great, thank you very much.
Okay.
Thank you very much for the nice talk. I actually also have a question about the dust input that you retrieved, which is, it's great that you got a number just to constrain that. My question is about the size of the particles. That when do you actually take those into account? Because if I understood correctly, you from that you take a part of that total amount, what is gone into the layers, but you show that ablation depends a lot on the particle size. And also you are saying that this changes with season. So I am puzzled of how actually you can get a contribution if you don't know exactly the size of the particles.
The size distribution of the incoming particles comes from this model of dust sources in the solar system, so the main comets that are producing dust and so on. So these particles are launched from the comet, and then they travel into the inner solar system under Poynting-Robertson drag and so on. Of course, they undergo collisions, and that reduces their size. So the size does change depending on how long, and we're talking about 100,000 years or something in the solar system. And sure, this is not terribly well known, because the only thing we can fit to is the zodiacal light at the moment, and that's, there are many ways of interpreting the signal that you see from that. It's not a very refined measurement, but that's why we decided in the end just to use the vertical flux of sodium and iron, because that's measured, and the cosmic spherules at the surface, because they are a measure of slow-moving particles that melt but don't completely evaporate. That seemed to test a few things. It's very hard, though. There is a new collection of micrometeorites and spherules provided by the French group in Paris, and that's a bit different from the South Pole, and we're trying to work out why. They have a different estimate, which is 3 times bigger, and what does that mean? So I didn't want to indicate that this is a solved problem at all, but that is currently our best estimate.
I have a fast question. Raised my attention the nickel problem that you mentioned. The problem is, if I understood correctly, is that the abundance of nickel do not match with the abundance of iron. But you always compare it with the chondrite abundance, chondrite meteorites. The other place that I know that you can find nickel with iron is in the nucleus of differentiated asteroids. That if you break it up, you can have very small pieces of iron meteorites. What happens if you take into account this in the abundance?
I think it will be, if you had just an iron meteorite, yeah, sure, but the amount of nickel in there is still a lot. It's not a 1-to-1 ratio. No, I mean, we're sure that measurement made in Alaska is wrong. We don't understand why, because with LiDAR, you fire the laser up, and if you see light coming back from a certain height, something is fluorescing. So it's actually very strange. I mean, there are other things in the UV, of course. Molecular nitrogen has excited states which will fluoresce at that wavelength of 337 nanometers. So that is a mystery. I was sure because I encouraged the people in Alaska to make the measurement, and when they sent it to me, I said, this has to be wrong. But, they went ahead and published it, and that's fine. And I guess we got our new project funded on the back of it, but...
Maybe because there are iron meteorites also?
I still think, though, that would just create... I mean, unless you have a source where nickel is the same abundance as iron, you have a problem.
What about space junk?
Yeah, space junk is an interesting thing, and that might be the reason why the Alaskan measurement is wrong. I say that humbly because I believe our measurement is correct.
So thank you again, John.